Okay, we're going to analyze and graph the rational function in example 1a from notes 4.2 day 1. We're going to do the same analysis that we've been doing, finding x and y intercepts, asymptotes, and holes. And what's going to be new is that we're going to take that analysis so that we can graph our function. Over here, you'll notice we have a chart where we can summarize the analysis. So we're going to begin by finding the x-intercept for this graph. To find the x-intercept, we're going to find the x values that make the numerator equal to 0, but ensuring that the denominator is not equal to 0, because when the denominator equals 0, the function's undefined. In this case, the numerator is equal to 0 when x is 0. So we have an x-intercept at the ordered pair 0, 0 with odd multiplicity because the x in the numerator only occurs one time that factor. And I'm going to summarize it in our table. So x-intercept 0, 0 with odd multiplicity. Next, let's find the y-intercept. The y-intercept is the point that occurs when x equals 0. So we're going to find f of 0, which is 0 over negative 1, which equals 0. So the y-intercept is the point 0, 0. And whenever we have an x-intercept at 0, 0, we're also going to have a y-intercept at 0, 0. Next, we'll go on to vertical asymptotes. Vertical asymptotes occur when the denominator equals 0, but the numerator is not equal to 0, or if they're both equal to 0, the multiplicity of that factor is greater in the denominator than in the numerator, which we can just say if we can't cancel the factor out of the denominator, then we will have a vertical asymptote. In this case, we have a vertical asymptote at x equals 1/2 coming from the factor 2x minus 1, and it has odd multiplicity because 2x minus 1 only occurs once in the denominator. So I'm going to summarize that in the table. Holes. Holes occur when we have a common factor in the numerator and the denominator. So we're looking for common factors. Here we have no common factors in the numerator and the denominator. So we have none, no holes. I'm going to put that over here. None. Last part of the analysis, or second to last part of the analysis, is we're going to be looking for the infinite asymptote, or the end behavior. What happens to our graph as x goes to plus or minus infinity? So the infinite asymptote, to determine what type of infinite asymptote we have, we're going to look at the degree of the numerator and the degree of the denominator. In this case, the degree of the numerator is 1, and the degree of the denominator is also 1. So n equals d. When n equals d, the degree of the numerator equals the degree of the denominator. We have a horizontal asymptote, and its equation is going to be the ratio of the leading coefficients, which in this case is 1/2. So we're going to have a horizontal asymptote at 1/2. We will not have a slant asymptote. We cannot have both a horizontal and slant asymptote. And the last thing that we want to determine is, does the graph intersect the horizontal asymptote? To find that, we're going to set the original function, which is x divided by 2x minus 1 equal to 1/2. When we solve this equation, we're going to find out that 2x equals 2x minus 1, which has no solution, so there are no intersection. So we're going to put none. Our graph does not cross the infinite asymptote. Now we're going to begin our analysis, our graphing, using this analysis. So I'm going to first plot the intercepts. In this case, we only have one. The x-intercept coincides with the y-intercept. That occurs at 0, 0. And I'm going to put a little O next to it to remind us that that x-intercept has odd multiplicity. And what we're going to learn today is that when we have odd multiplicity for an x-intercept, that means that the graph crosses the x-axis at that x-intercept. And if we have even multiplicity, then the graph bounces at that x-intercept. Okay, so we're going to use that in a minute. Then we'll put on our asymptotes. So here we're going to put on our asymptotes at x equals 1/2, the vertical asymptote. So I'm going to go ahead and sketch that in with a dashed line to denote that it is an asymptote and not truly part of our graph. I'm going to put its equation, x equals 1/2. And up here, I'm going to put a little O to remind us that that vertical asymptote has odd multiplicity. And then I will also sketch in the horizontal asymptote, which is at y equals 1/2. So this is the skeleton of our graph. And from this amount of information, we can sketch our entire graph. So we know that at this x-intercept with odd multiplicity, the graph must cross the x-axis. And we also know that our graph never crosses the horizontal asymptote at y equals 1/2, which means that our graph has to cross the x-axis here, approach that horizontal asymptote as x goes to -infinity, and then it's going to shoot down as it gets close to the vertical asymptote at x equals 1/2. Now we need to learn what it means when we have odd multiplicity of a vertical asymptote. When a vertical asymptote has odd multiplicity, that means that our graph also crosses the x-axis when we go across that vertical asymptote. Or you can also think about it as the ends of the graph going in opposite direction when we cross the vertical asymptote. So here the graph was shooting downwards. When we cross the vertical asymptote, the graph is going to be shooting up. Okay, so if we have odd multiplicity, that means that the graph crosses the x-axis. If we had even multiplicity for our vertical asymptote, the ends would stay in the same direction, and we'll see that in other examples.